Okay, in previous lessons, we have talked about the idea of the double integral and how to do it over some specific regions. Specifically, we did it over rectangular regions to start, and then we did it over um, regions where you had some kind of two different functions that the base region is going to go between. Now the question becomes, what if the domain is more easily described in polar coordinates? So, just kind of refresh. In polar, we're talking about things which are basically circular. So, if we kind of have this idea of a circle, standard equation of a circle centered at the origin is x squared plus y squared equals the radius squared. And in this case, we're just going to call our radius 1. So we'll say that this has goes from 1 to negative 1. And the idea is we could do this in rectangular, and we actually have in the past. If we did this in rectangular coordinates or Cartesian coordinates, same thing, rectangular coordinates, x would vary from here to here, which means it's going to go from negative 1 to 1. So we'd have to take a double integral from negative 1 to 1. And then y is going to go from the bottom of the circle up to the top of the circle. And if we kind of go back and solve the circle in terms of a function of x, that would be what, y squared equals 1 minus x squared. Take the square root. Y would equal the plus or minus square root of 1 minus x squared. So really, this thing would vary from the negative square root of 1 minus x squared to the positive square root of 1 minus x squared. And then whatever the function that's floating up in space would be our z value, or your height of this thing. That would be your function of x and y. And we just said that we had to do that dy dx, because that would be a type 1 region where we're going from the function at the bottom to the function at the top. So this could be done in rectangular coordinates. Well, it's a circle, so if you think about things in circles, a lot of times polar is just easier. So if we did this as a polar region, polar is going to be some kind of r theta. If you remember back to your calculus ABBC training, polar is done in r theta. Well, if you look at the circle here, it really isn't that difficult to figure out. R, the radius, put this in green, the radius is going to go from here out to here. The radius is basically going to vary from 0 out to 1 in this case. So when we come down here, oops, nope, don't want that color. So our radius is going to vary from 0 to 1. And theta, well, that's pretty easy, because theta is going to go from here all the way around to here and back. So it's going to go full 2 pi. So theta is going to go from 0 to 2 pi. And I'm going to have some kind of a function of r and theta. The question is, what is this out here? It's not just going to be dr d theta, it's actually going to be something else. And while I could very easily just give you what this is going to be, um, I'd rather show you actually where this is going to come from so you have somewhat of an idea. I could literally just tell you what this is out here, and you'd be able to do these problems without too much of a difficulty. But the general idea is that, I mean, you guys know I would like to show you, I want to show you where it all comes from. All right, so I'm going to actually skip to the next page to do that. Okay, so how do we come up with this formula for integrating in polar? Well, if you think about what the general idea was, oops, not writing, there we go. What the general idea was in rectangular. So have some kind of a space function of z, and we're going to do this maybe over this rectangular region right here. I'm not exactly sure what it's going to look like. But, you know, your rectangular region will connect here, 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 and there. So there's your rectangular base in the XY plane. That's kind of your domain. And then you've got your Z value. And remember what the idea was. You're going to take all of these little um, rectangles in the base. So we'll get, you know, a ton of different little rectangles in the base here. And this distance right here, because it's in the x direction, is some kind of a delta x or dx. And then this distance right here, because it's in the y direction, is going to be your dy. And if we took that region and we extended it vertically up to the actual surface itself, what you would get is some kind of a volume, because you're going to include the height now, which is your z value. So this thing right here would be pretty much that z equals h. It's just going to be the height of the space curve, whatever this surface is up here. And remember that this rectangular prism that's formed here, the volume of a rectangular prism, of course, is length times width times height. So when we did a double integral over our domain, over our rectangular region, in this case the domain, it was whatever the function of x and y is, which is your z value, it's this thing right here, and then the dx and the dy, or the dy and dx, it doesn't really matter, was your length times your height. I'm sorry, your length times your width. So this stuff right here was basically the LW part. That's what this was, right there. And then h, again, h is your z value. Whoops, that was supposed to be green. So h is your z value, right there. All right, and that's how we did it in rectangular. Don't like the thick pen. Switch out of that. All right, but now let's think about this in polar. First of all, most of the time when we do this stuff in polar, it's going to be in some kind of a circular base. So let's go ahead and kind of sketch what that would look like. And by the way, this will probably take it's definitely going to take 3 videos. I might do a 4th, we'll see. So the idea is we're going to have some kind of a domain which is circular. I'm only going to do the first octant here just to kind of give you an idea. And then maybe there's another circular region here. And what we're going to have is this this is going to be your domain on the base. And if this thing were to extend vertically, see if I can sketch this well, looks something like that. And then if this one extends vertically, yeah, there we go. So what I've got is I've got this region here. Let me close this off so you can kind of see the entire region in red there. You kind of have this, it looks almost like a washer. It's got a pretty big thickness, but we've cut only a certain part of the washer. It looks like a quarter of the washer, with it's pretty thick actually, because if you extended this whole thing around, you'd have an open circle right in the middle. But the idea is now we're going to take and create these little sectors. So I'm going to have a rectangular region here, another region there, another region there, another region there, all the way over to the other side. And if I took one of these little regions right here and extended these up to the top, what we're going to have is basically these little rectangular regions right here, but these are going to be polar rectangular prisms of some kind. So that's the general idea. This is what we're going to actually be doing to try and find the volume. We're going to take all of these, infinite number of these things between, here and here, and then add them up this way and this way. So let's kind of look at what the domain would look like if it's just in 2 dimensions. So we're only talking about the first octant, which is really just going to be the first quadrant. Whoops. There I go again. I got to figure out how to change this thickness permanently. Whoops. Thought I did it. Guess not. There we go. Okay. So this is going to be our domain of this region. And the first one, we'll just say that the first one has a radius, that's horrible, a radius of 1. Okay, that's better. And then we'll say that the second one has a radius of 2, and that's not good. Let's try it from here. Close enough. So we'll say that that's 1. We'll say that that's 2. And again, so the general idea is on the base of this thing, we're going to take and we're going to divide up. This will be interesting to see how well I can do this. We're going to divide, that's not good. We're going to divide this into a whole bunch of radii that go from 1 to 2. All right, we'll try and leave it there. And then we're going to take a whole bunch of angles, and we can put, an infinite number of angles. An angle that's going to be here, an angle that's going to be here, another one here, and here, and so on. So, we're going to take an infinite number of angles that extend out to the outside radius. And what we're going to focus on, okay, I used everything but green. Let's use green. What we're going to focus on is this one particular section right here. Okay, that circular or polar wedge, we're going to focus on that one right there. So what we really want to do is we really want to find what the area of that little piece is right there. So what we're going to have is we're going to have some kind of a double integral of f of r theta. And remember that f of r theta, that's going to be this piece up top in here. That's going to be this part that's floating in space. That's basically your height. And then we're going to have the base, which is going to be the area of the polar piece, or this little polar wedge right there. And if we add up all of those polar pieces times the heights, then we should get the volume in the polar region. So one thing that we need to recall in order to show how this is going to work. We need to recall, and you may or may not remember this, that the area of a circular sector is 1/2 theta r squared. Okay, that is 1/2 of a, here, let's put this in here, circular sector, there we go, is 1/2 theta r squared. And while this next part is not really a proof, it does show you that at least it works for stuff that we know. If you think about the area of a circle, a full circle, we know the area of a full circle is pi r squared. Well, if you think about it, theta there would be 2 pi, right? So that's the same thing as 1/2 if theta is 2 pi, because we're talking about a full circle, r squared, then the 2 pi and the 2 cancel out, and you just get pi r squared. And again, you could show that for any piece of an entire circle. So if I wanted you to find the area of the circular sector of pi, pi thirds radians, you would plug pi thirds in here, and then you would get, pi sixth r squared or something like that. All right, so in general, this is what we need to be thinking about. If I want to find the area of that green piece right there, we're just going to isolate the sector that has that green piece in it. So it's going to be created by having, one piece here. Whoop, too long. And then one piece here. Wow, that's just not good. There, that'll be a little bit better. All right, and what we're going to focus on, let's go back to green, is this piece right here. That region right there. So if we want to find the area of this circular sector here, well, it seems to me that if we can figure out the area of the entire wedges and then subtract off the area of this inside wedge, this white piece, then we'll get the area of the green circle. So let's label some things here. This thing right here, from here out to here, it has a radius, and I'll just call this one r sub 1. And then this piece right here also has a radius, and we'll just call this one r sub 2. And so the concept is, if I take the piece of the sector that has r1 and I subtract the piece of the sector with r2, then I should end up with this piece in here, which is green. So just kind of sketching the general idea here. Oh well, just going to deal with the thickness here. If I take this wedge, which has the r1 part of it, that would be, no, I'm not going to deal with the thickness. This would be, let's do this in red, since we're dealing with r1. This would be 1/2 r1 squared d theta. And where does the d theta come from? D theta, let's do it in purple, give it a little bit different, comes from right here. This change right here is the change of your angle, so that's d theta. So the change in here, the change between the two angles, is d theta. So 1/2 r1 squared d theta minus, well, what if we took the smaller region, which maybe is this piece right here, and of course this one has to do with r2, which we did in blue. So that would be a 1/2 r2 squared d theta. Well, that should give us, if I take this region and I subtract this region, that should give us that piece right there. Should have put it in green, I guess, since that was our initial green piece up here. All right, not the prettiest, but you get the idea. And so what that's going to be, let's see, if I take this and subtract this, let's see, I've got a 1/2 in common, I've got a d theta in common, I can factor those out, so I've got a 1/2, and then d theta can be factored out. Then I've got an r1 squared minus r2 squared, so r1 squared minus r2 squared. All right, and so how are we going to deal with all this? Well, let's write this here, 1/2 r1 squared minus r2 squared d theta equals 1/2 d theta. I'm just moving the d theta to the front. This is the difference of squares, so it factors. That's going to be r1 minus r2 times r1 plus r2. All right, so what is the difference in the two radii? Well, if you think about it, the difference between the two radii is the change of r, or dr. So not much of an issue there. I'm going to get 1/2 d theta dr. Looks like we're getting somewhere because I'm pretty sure these two things are going to have to be in the equation. But this piece over here. Okay, so just like everything else with calculus, if you think back to the BC stuff, remember that we're trying to let these two things get so infinitely close to each other that they're basically the same without actually being the same, but they're so close, what we can really say is that R1 is approximately equal to R2 because they're getting super close to each other. And if that's the case, it doesn't really matter which one we use. We could use R1 or R2, but really we would have R1 plus R1 or R2 plus R2 because they're basically the same thing. So because of that, we're just going to call them R. And so if I let R plus R go into here, we're going to call it 2R. R plus R would be 2R. And then obviously these 2's cancel out. And what I end up with, finally, oops, after all this, let's go with red. Finally, what I end up with is the double integral of the function of r theta. Again, that's your height. And what I have left here is an r dr d theta. R dr d theta. Where this, again, is the height. And all of this is the area of one slice of D. And this right here is the equation for a double integral in polar. So really, again, I could have just told you that this part right here was r dr d theta, but you can see it's definitely not just dr d theta. I could have just told you that, but at least this gives it some kind of a meaning as to where it comes from. All right, that's about almost 24 minutes. We are going to come back with a second video and do examples.